In this module, we will learn about energy. Energy is the capacity to do work, and energy can exist in various forms. Some of the examples are heat energy, wave energy, kinetic and potential energy, electrical or sound energy. And energy cannot be created or destroyed, but it can be transformed from one form to another. Here's an example of energy conversion in the context of generating electricity. So you have heard about hydroelectricity and also wind energy, like in the windmills, as used in the windmills. So in the windmills, the kinetic energy of the wind is converted into electricity, and for hydroelectricity, the energy of falling water, as in waterfalls or dams, is converted into electricity. Then another example is chemical energy, which is typically stored in a battery, for example, and when the battery is connected to an electrical circuit, it can drive a current through, and so it has some electrical potential energy that is stored there. A common form of energy is heat energy. So when a light bulb is on for a long time, it heats up its surroundings. The sun emits a large amount of heat energy, for example. So heat is typically considered to be a waste form of energy because it is not easy to harness heat energy. But it can be useful in certain cases. For example, in cold climate, heaters can be used to warm up our surroundings. So what are the units of energy? So energy is a scalar quantity. The unit is a joule, and 1 joule is defined as 1 Newton times 1 meter. The unit of energy is joule, and it's Newton times meter. And as we know, Newton is kg meter per second square. Then we have to come to the definition of work. Work is the process of energy transfer. For example, if you want to change the energy of an object, you have to perform work on the object. If the work is done on a system, we call it positive work, and energy is transferred to the system. If you do work on a system, you give the system more energy. And if the work is done by the system, then it is called negative work. And in this case, the energy is transferred from the system. The energy is transformed out of the system, basically. So in physics, we define work as the dot product of the force and the displacement. For example, if you apply a force to an object and the object undergoes a displacement delta r, as shown in this figure, the work is given by the dot product, a scalar product of the force and the displacement. And remember from our discussion about vectors, so if you take the dot product of two vectors, you get a scalar quantity. So work is a scalar quantity, and its unit is the same as that of the energy. It's a joule. And so basically, because of the dot product, the work is given by F, the force, times the displacement delta r, times the angle between the force and the displacement. In this case, it's cosine of theta. So you can see that if the displacement is 0, if I am applying a force, but the object is not getting displaced, the displacement is 0, then no work is done actually. Delta r is 0, right? An example is if I push on a wall and the wall does not move, then I am actually not doing any work on the wall. Also, if I apply the force perpendicular to the displacement, then there is no work done also. The work done is 0 because cosine of 90 degree gives you 0. So then let us discuss kinetic energy. Kinetic energy is the energy associated with translational motion. So if a particle of mass m is traveling at a speed v, then the kinetic energy is given by k equals half mv square. And how do you change the kinetic energy of an object? So you have to change the speed of the object, and you can do that by doing work on the system, because work is the process of energy transfer. So if you transfer energy to the system, its velocity can change. So the kinetic energy can change. And this brings us to the work kinetic energy theorem, so which basically states that if you perform work on a system, it goes into changing the kinetic energy of the system. And let us derive this in the case of a very simple 1D example. So a force is acting in 1D and causing an acceleration of an object ax, and for simplicity we will assume that the acceleration is constant. So in terms of Newton's second law, this is just F equals ma, just in one direction, the direction x here. And also we will invoke an equation from our study of kinematics, from the kinematics module. And this is because the acceleration is constant, we can write the final velocity squared, v square equals v naught square plus 2axd. Here v naught is the initial velocity, v is the final velocity, ax is the constant acceleration, and d is the displacement. And then if we multiply both sides of this equation by half m, then we get something like this, half mv square, and we rearrange one of the terms, half mv square minus half m v naught square equals m times ax times d. And we can immediately see that max is actually equal to fx from Newton's second law. So we can substitute f in terms of instead of max, and we have half mv square minus half m v naught square equals fx times d. And fx times d is just the work in this case. It's a 1D problem, very simple. The force is in the x direction, the displacement is in the x direction. So fx times d gives us the work. And from the expression of kinetic energy, we have just shown half mv square is the final kinetic energy, and half mv naught square is the initial kinetic energy. So the left-hand side of this equation is just the final kinetic energy kf minus the initial kinetic energy ki. So the change in kinetic energy delta k is equal to W, the work done. So this is the work kinetic energy theorem, a very useful tool in solving problems. And so we have talked about kinetic energy associated with translational or sliding motion, but there can be other forms of kinetic energy. Kinetic energy is just the energy associated with motion in general, and the motion can be of different types. For example, a particle can be rotating or spinning, so there is a rotational kinetic energy associated with the particle. Some particles can vibrate. For example, two atoms vibrate. For example, a diatomic molecule can vibrate about a center, for example. So they have some vibrational energy associated with them. A ball rolling down an incline has both rotational energy and translational energy combined. So it is possible to have multiple forms of kinetic energy at the same time also. So in this course, we won't be talking about rotational and vibrational kinetic energy, but we'll mostly be focusing on translational kinetic energy. And so let us now look at another example, a case of a spring, the type of force that is developed when a spring is pulled or pushed. And so far in most of the examples, we have considered the case where the applied force is constant. But in this case, we will see that F itself is a function of displacement. And so if you attach an object to a spring and pull the spring, you feel that there is a tension in the spring that tries to bring the object back to its rest position. So if you are displacing the object to the right, the spring tries to bring the object back to the left, to the rest position, right? So this force is then acting opposite to the displacement. And then if I compress the spring by pushing it to the left, then the spring tries to push back to the right, back the object to the right. So the force again, because the displacement is negative in this case, the force is acting in the opposite direction, in the positive direction. So we see that the force here acts always opposite to the displacement. We can write this type of relation by this equation F equals minus kx, because the larger the displacement, the stronger is the force. But the force always acts opposite to the displacement. And K here is the proportionality constant, also called the spring constant, given in Newton per meter. So this equation is called Hooke's law, basically, and it applies to systems like springs, basically. So, and this is a case where the force actually depends on the displacement. More the displacement, the more is the magnitude of the force. But in this case, the force acts opposite to the displacement. So if you pull the object to its maximum position, to a certain position, and release it, the object begins to oscillate back and forth. So the spring gets pulled and compressed, stretched and compressed, and the object keeps oscillating back and forth. So let us work out expression for work in this case. For example, if I stretch the spring, pull the object to the right, and then release it, the spring takes it back to its rest position. We will evaluate the work done in this process from x max, from a displacement of x max to 0. So we can still apply the dot product, but in this case, because the force is changing with the displacement, we have to be a bit careful. We have to take small infinitesimal displacement of the block, and then add up all these infinitesimal displacements. So we still have the dot product f dot dx. Dx is the very small infinitesimal displacement of the object, but then we have to integrate. Adding up all these infinitesimal displacements mean we have to integrate. So we integrate from the initial position x max to the final position 0, and then instead of f, we put Hooke's law dx. And remember, the dx here is acting to the left. The force is also acting to the left. So the cos theta gives us 1. Cos of 0 degree gives us 1. And we substitute minus kx for f. And we perform the integration and evaluate over the range x max to 0. We get something like half k times x max square. So this is the work done by the spring on the object as soon as I release it from its maximum position and it reaches the equilibrium position. So this expression can also be related to potential energy, because when I am stretching the object to its maximum position x max, it has some stored energy, right? Because if I release it, the spring can do some work. So this is what is called potential energy, which we will go into details in the next slide. And what is the total work done on the system if the object goes from the maximum positive x displacement to maximum negative x displacement? It is 0, as you can see. Now let us discuss potential energy. Potential energy is basically a stored energy that has the potential to do work. When energy is given to an object, it can be stored up, and then upon release, the energy can be released and transformed into some other form. For example, kinetic energy or heat energy. And examples are, for example, in elastic potential energy, the case of the spring that we have seen, or the gravitational potential energy, as we will see, also the electric potential energy. These are some of the examples where potential energy plays a role. Gravitational field analogy. Now suppose I have this object in my hand, and I lift this object to a certain height. Compared to its initial height, I have lifted it by a certain height. Now, in doing so, I have applied a force that is directed vertically upward, and the displacement is also vertically upward, right? So from the dot product, the angle is 0, and both the displacement and the force is in the positive y direction. So I have done positive work on the object. That means I have transferred energy into this object. Now this object has some stored energy, and this stored energy is in the context of the gravitational field that is around us, because it is being pulled by the force of gravity, and if I release it now, it falls, right? And so in doing so, it speeds up. So when it is close to hitting my hand, it has a larger velocity, it has a larger kinetic energy. So this stored energy, when I release the object, that energy is released and converted into kinetic energy. And this happens because the gravitational field is doing work on this object when it is falling. Now let us look at the expression for the potential energy due to the gravitational field. And the potential energy U is represented as U. It's given by m times g times the height the object is displaced to, basically. So it has some initial height, and I take it to a final height. I call it y naught and y, and it is the difference in this height, basically, represented as delta h or simply h. So U equals m times g times h. M is the mass of the object, g is the acceleration due to gravity, and height is the vertical displacement I have lifted the object through. So this is the expression for the gravitational potential energy, the potential energy that is stored in an object when it is displaced to a height h. So let us talk about energy conservation in this context. So you have seen, like, when the object is lifted to some height, it has some potential energy, and initially it is at rest, so it doesn't have any kinetic energy. Its velocity or speed is 0. Now when I release it, it falls to my hand, and the moment before it touches the hand, it had the highest velocity or speed, so it had the highest kinetic energy. And when it reached my hand, its potential energy was 0 because I have taken my hand as the reference point, the initial position. Right? So I can see that at the highest height, the object had the highest potential energy and 0 kinetic energy. And when the object fell to my hand, it had 0 potential energy and maximum kinetic energy. And if we neglect air resistance, when like the object fall, it can hit air molecules. But if we ignore that process, then actually the total energy is constant in the system. The total energy is the sum of the potential and the kinetic energy. So whatever it was at the beginning, it is also the same at the end, basically, just before the object touched my hand. So this is called conservation of energy. So it is given by the total energy. Total energy is the sum of the kinetic and the potential energy. So the total energy at some initial instant is equal to the total energy at some final instant. So at the final instant, it's given by Kf, the final kinetic energy, and the final potential energy, Uf. So when this equation holds, we say that energy is conserved. So energy can still be converted from kinetic to potential energy, but remember the total energy is remaining constant in this case. So this energy, so there are certain types of forces which actually maintains this energy conservation law. So these are called conservative forces. For example, the force of gravity is a conservative force because it maintains this equation. We saw that the total energy was remaining constant, although it was getting converted from potential to kinetic energy, but the total energy was remaining constant. But there are some forces which do not maintain the energy conservation equation, and these are called non-conservative forces. Some examples are friction. When an object is sliding on a surface, rough surface, there is frictional force, as we have seen, or the air resistance that we neglected in this problem. These create energy dissipation, basically, and they are non-conservative forces because the energy lost to them cannot be easily recovered back into the system. So basically, it all depends on the definition of system. For solving problems, we have to define a system. And in this case, if our system just contains the force of gravity, for example, we see that it is a conservative force and the total energy is remaining constant. Now, if we add another object to this, for example, if we transfer energy out of this system, then the total energy of the system changes. It doesn't hold. For example, if we take into account air resistance now, so actually some energy, as the object is falling, some energy is lost due to heat energy with collision of with the air molecules. So this is getting lost from the system because my system only consists of the gravitational potential energy as I have defined it. And this non-conservative force, the air resistance, is taking this energy out of the system. But if I define my system in another way, suppose my system consists of both the air resistance and the gravitational field, that is one conservative force and another non-conservative force, then still the total energy inside the system is remaining constant. Some energy is being lost from the gravitational field, but that energy is going to heat up the air molecules, basically. So as a whole, within the system, my total energy is remaining constant. That's why we say the total energy is neither created nor destroyed, but converted from one form to another. So in solving problems, we have to define our system carefully, and then the solutions will become easy, basically. But as you can see, energy conservation is a powerful technique for solving problems because you just need to consider two instances, an initial instant and a final instant, and evaluate the energy expressions in those two instances. Whatever happens to the particle in between does not matter so much. So this can be a powerful technique to solve a number of complex problems. And now let us look at the definition of power. Power is the rate of energy transfer. Basically, it's the average power is defined by as the work done divided by the time interval in which that work is done. So it is the rate of energy transfer. And power has the unit of watt. It's called watt. And watt is just joules per second. Power is a very important metric when we consider energy because many of the definitions, like when you pay your electricity bills and everything, gas bills, for example, you have to consider the units in watts, basically.